to the Journey Shake Chem. Today we're reviewing how to write complete electron configurations. So you need to use your diagonal rule to do those, and ending electron configurations. It's good review. So please do those two questions in your composition notebook to the best of your ability, and we'll discuss them in a moment. In question number 1, we are reviewing complete electron configurations. And I hope you have your diagonal rule there to help you along with this. I have to use the diagonal rule because I can't remember the order in which the electrons fill the orbitals. Lowest energy, and it's not always in the way that we expect it. So I write my first energy level has an s orbital, maximum 2 electrons. The second energy level has an s orbital and 3 p orbitals. And remember, each orbital can only contain 2 electrons, giving me a maximum of 6 in the p sublevel. The third energy level has a s orbital, the p orbitals, and then the d orbitals. And there are 5 d orbitals because I have a maximum of 10 electrons. In the fourth energy level, I have the s, the p, the d, and I pick up the f. And there are 7 f orbitals. Having 2 electrons each gives me 14 maximum electrons. And then the 5th, 6th, and 7th energy levels just follow the same pattern. Then I draw my diagonal line through 1s2 and 2s2, and after that it just follows. And it gives me the order in which the electrons will fill the energy levels and sublevels. Well, my first one that I have to do is sulfur, which is atomic number 16. Well, it has 16 electrons and 16 protons in the neutral atom. I need to add up, go to the maximums in my diagonal rule until I get to 16 electrons. 1s2, 2s2, 2p6, 3s2, and 3p4. And if I add these up, I get 16. 2, 4, 10, 12, and 16. Barium has atomic number 56. It has 56 protons and 56 electrons in the neutral atom. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, and 6s2. And if I look at barium, it's on the 6th energy level, and the outermost electrons are on the 6th energy level. And that's a good double check. If I add up the numbers, they should come out to 56. 2, 4, 10, 12, 18, 20, 36, 38, 48, 54, and 56 is how many electrons that barium has in the neutral atom. Then we have calcium, and that's a little number. It's a little easier, isn't it? Well, we have 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. And calcium ends in 4s2. It's in the 4th energy level if I look at it on the periodic chart. 2, 4, 10, 12, 18, and 20 electrons. And then finally here we have xenon, which is atomic number 54. It has 54 protons and 54 electrons in the neutral atom. And the reason that I say the neutral atom is because some of them can form ions where they gain or lose electrons. But we do not see a charge on any of these, and therefore the atom is neutral. Well, we need 54 electrons, and we follow the diagonal rule. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and 5p6. And I noticed on xenon, it is in the 5th energy level, and we only count the outermost electrons, the highest energy level. And we'll see that in number 2. Number 2 asks for the ending electron configurations. And when I look at the ending here, for sulfur, I'm on the 3rd energy level. The outermost valence electrons would be s2p4. In barium's case, the highest energy level that I'm at is the 6th energy level, and therefore the S2 is my ending electron configuration for barium. Calcium, the highest energy level here is the 4th energy level, and it also ends in S2. And I see that barium and calcium are in the same group, the same column. Xenon ends in S2P6. We only take the highest energy level. These 4D10, they don't count for valence electrons because they are lower energy, and therefore it is S2P6. And that's the ending electron configurations for those elements. A bit of review from yesterday. Well, get out that periodic chart. We're going to put some more notes on that blank periodic chart. So I'll be right back. The blank periodic chart that we have is very useful to take notes because there's a lot of things that we need to learn about the periodic chart and how the elements behave. Well, we'll review a little bit and add a little bit more to what we already know. In the very first column, we know that the ending electron configuration is S1. Everything in this column will end in S1. Everything in the second column will end in S2. And we call these two columns the S block. However, it's important to remember that helium is also part of the S block because helium has an atomic number of 2. And therefore, its complete electron configuration is 1s2. And when it has those 2 electrons, it fills that first energy level. And therefore, it has a noble gas configuration, even though it doesn't have an S2P6, which is what most noble gases will have, except for helium. Then, so that is called the S block. Then we jump over to the other section that we've talked about, the P block. These 6 columns are in the P block, and it goes S2P1, S2P2, S2P3, S2P4, S2P5, and S2P6. And S2P6, when we add those two numbers together, we get that there are 8 dots, which is an octet, which is a very stable, low energy configuration for an element. And these 6 columns correspond to the 6 potential electrons that fill those p orbitals. And we call this section the p block. Then in the center we have the d block, and these are filling the d electrons into those d orbitals, and we have a section that has been taken out and put on the bottom, and that's filling the f block. And you'll notice that there are 14 columns in the f block, which correspond to the maximum of 14 electrons that can fill into those f orbitals. And 10 columns for the d block. That is for the 10 possible electrons that can fill those d orbitals. Now, the D block is also called the transition metals. And the reason that we take the F block out is so that we can fit it on a regular sized piece of paper. Otherwise, we'd have to have a legal size. And these are not used very much, these F block atoms, and therefore we can take it out and put it down on the bottom. They are called the inner transition metals. And they also have another name of the lanthanides and actinides. And that corresponds to the very first element that is found in those F block periods. Now I want to talk a little bit about the D block. And when we fill the electrons, and the ending electron configurations here would be S2D1, S2D2, S2D3, and then we would expect it to have S2D4. But when we look more closely at the arrangement, well, when we have S2D4, it would look like this. And these are called orbital filling diagrams. And oftentimes we see them actually as blocks, but I prefer lines because I don't want to write all the rest of the sides of the block. This works just fine. And this would be D4. And we fill 1 electron per orbital because you'll remember the school bus rule or Hund's rule that everybody wants their own seat until they're all filled, and then you have to double up. Well, this is what it seems like it should be. However, when we look at the S1D5, it would look like this. S1D5. 1, 2, 3, 4, 5. And in this way, they're all spinning in the same direction. And when electrons are all spinning in the same direction, it's lower energy. And this is very much like if you're going in a marathon and everybody's riding their bicycle or even running in one direction, and then one person comes back the other way and everybody just gets all discombobulated. Well, we just can't have that. It's just going to be this one person here is out of the norm with everything else. And so it mixes everything up. So it's much lower energy if everybody just goes the same old way. Yep, that works better. And so this is lower energy, and that's what electrons will always do. And therefore we have S1D5. And then we have S2D5. And then S2D6, S2D7, S2D8, and then again, we run into an exception. Well, we would think that we would have S2D9. S2D9. We have the 2 s electrons. We have 5 d orbitals, and they can each have 2 electrons. Well, we add 1 per orbital until each one has 1, and then we come back. And it would look like that. S2D9. Well, when we compare it to S1D10, we see that it looks like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In this way, the d orbitals are all spinning in opposite directions, which makes it very balanced. And the s and the d orbitals are like different houses, and they're completely different. And so this S2D9, this D9 is a little bit unbalanced, and therefore it is preferable that all the Ds have the electrons spinning in opposite directions. It's much more balanced, and this is actually the way the arrangement will go. And that is the other exception. S1D10 and then S2D10. This column here and this column here are exceptions in the D block. Now there's no such exception like this in the P block. It's only in the D block, and then later on you may learn about the F block, but we're not going there, so we're just concerned about the D block. Well, you'll recall that we said that the dot diagrams would have S and P electrons only. So when we do a dot diagram for these elements, in this column would only have 1 dot, because D as in dog, electrons are not in the dot diagrams. And so this column that contains chromium has only 1 dot. And this column that contains copper and silver only has 1 dot. And therefore we would write it as Cr with 1 dot and copper with 1 dot. Because the dot diagrams are for S and P electrons only. Those are the ones that are available for bonding. Those are our valence electrons. And the orbital filling diagrams is a way to describe why it is that we go this way for the lower energy rather than what we would expect. Now I want to revisit the idea of oxidation numbers. Oxidation numbers are numbers that tell us, will the element gain electrons or lose electrons? Well, when we had something gaining electrons, we got a negative charge. And when we lost electrons, we get a positive charge. Well, we're going to look at the general trend here, and there are exceptions that we'll get to later on, but let's just have some basics so that we can refer to them. Well, the first column is +1. It will lose 1 electron. And when I look at sodium that has atomic number 11, it goes 1s2, 2s2, 2p6, and 3s1, 2, 4, 10, 11. When it loses this 1 electron, what's left is an electron configuration that looks just like neon, a noble gas, and that's what they like to do. It's lower energy by losing this one electron. The second column would have a +2. Now the transition metals here have a variety of different oxidation numbers. Well, we're not going to include those in our oxidation number requirements at this time. Well, when we go to the S2P1, we're going to lose 3. And then we lose 4. Well, this, remember, is a general trend, and there can be differences, but for our purposes, this is what we're going to do. Well, in this column, we're going to gain 3 electrons. It's S2P3. By gaining 3 electrons, it will have an electron configuration of a noble gas, which is S2P6. And then the oxygen column will be -2. And then the next column will be -1. And then 0, the noble gases, and we're going to talk about these family names so that we know which ones we're talking about, that they don't want to do anything. They like being S2P6, and under pressure they can be forced to do some things, but they would rather just stay and do nothing. We understand that, don't we? Well, then I would also want to tell you that we have some very special line that we need to write here. I want you to make a very dark line on your periodic chart, very much like I have. And we go below the boron and down along the silicon, and then on the bottom of the silicon, and then down the germanium, and underneath the arsenic, and down the antimony, and under the tellurium, and then down to the bottom. That separates the metals from the nonmetals. Here, on this side, we have the metals. And then on the other side of the stairway, we have the nonmetals. And then these that are in between that I have written here, boron, silicon, germanium, arsenic, antimony, tellurium, and astatine, are called semimetals or metalloids. They have characteristics of both metals and nonmetals. And that way we separate the metals from the nonmetals. And here, that is a lot of material that we have discussed today. And I have one more thing to discuss, and that is the family names. Well, the first column, the S1, they're called the alkali metals. However, hydrogen is not in this group. Hydrogen is a non-metal, and therefore it is not an alkali metal. It's placed here because hydrogen only has 1 electron, and therefore its ending electron configuration is S1, and therefore it's placed in the column with the alkali metals. Then we have the alkaline earth metals. Alkaline earth metals. They have the S2 ending electron configuration. Then we jump all the way over to the last column, and that is called the noble gases or inert gases. Noble or inert gases. I always have a problem with LEs and EL, and I believe that that's correct. Then the next column, the S2P5s, are called the halogens. They are the salt formers. The next column are called the chalcogens. They are the chalk formers, chalcogens. And then these 3 columns, we don't really have a name. Boron, carbon, and nitrogen. That works just fine. There's no real technical name for those. That's a lot that we discussed today. And I believe that we've talked about everything that we need. You know your oxidation numbers, you know your dot diagrams, the family names, how to separate the metals from the nonmetals, and ending electron configurations for the D block and why we have the exceptions. Well, that was some fun, and thanks for being here, and I can't wait till tomorrow. Bye. Oh, wait, one other thing. You have a quiz tomorrow, a quiz on the 50 elements. I know you'll do well. You're going to get either the symbol or the formula. You have to go one way or the other. I give you the symbol, you give me the word. I give you the word, you give me the symbol. And this time, spelling counts. It's the only time of the year where spelling counts. I know you do well, and I can't wait to see you tomorrow. Bye.